This is an introduction to using the Symbolic Math library in Python. The library is called sympy, S-Y-M-P-Y. We use the library by typing from sympy import star, and then in order to set the best printing of output to get nice mathematical output, we'll call this function init_printing. There's a really great tutorial online that goes through this, and if we open the link, you can see what it looks like, and it goes through a lot of these different sections. I've kind of taken and simplified that down to a single notebook with most of the basic topics that they include, but it doesn't include as much information, so I recommend that you use that tutorial for a greater reference. Here we're talking about symbolic math, that is solving equations analytically to get formulations and optionally evaluate equations numerically. So this is like when you simplify an expression by hand or compute an integral analytically. It'll do the math for you. You need to define symbolic variables before you use them. So this is the main new thing with using this library, is you just need to tell Python that the variables that you're using are symbols. So if we want to work with symbols x, y, and z, for instance, we can call this function symbols. X, comma, y, comma, z equals symbols, and then in the quotes we're telling it what the variables are. And these are the variables that you'll be using, and these are what they're stored as here. So these x, y, and z will be sympy objects. We create a symbolic expression, and we can store it in some variable. So now that x is a symbolic variable, I can type my expression, my x, equals x times cosine x, and it will be a sympy expression. And let's go through and run these. So if we come here and go my x, it will output, give us the symbolic representation for that expression, which is x cosine x. So this is how we store the expression. And then if we want to see what the expression is, we can just type my underscore x here. That works just fine. Let's cut that out. So substitution is a really common thing to do. This would be substituting a symbol or a number in an expression. So for this we use the subs function, and we would call that with my x.subs. X is what I'm subbing for, and 1.0 is what I'm going to substitute in for x. So here we have x cosine x. I'm going to substitute 1 for x. And when we do that, if I substitute it with 1.0, it says, okay, let's evaluate that, and it does it numerically and gives us the answer. If we just type 1, then it's going to sub in cosine of 1. We can substitute y for x. Y is just another symbolic variable, so we can do y. And when we do my x subs xy, we're substituting y for x, and the output is y cosine y instead of x cosine x. Notice that this doesn't change, this won't change my x. If we do my underscore x, then we still get x cosine x, because we haven't reassigned my x. We're just looking for what my x gives us if we substitute y for x. So if you wanted to reset it, you would type my x equals my x dot subs x comma y if you wanted to reassign this my x variable here. We can substitute more than one thing at once. So suppose my expression was x squared plus 2xz plus minus y. We could substitute in values for x, y, and z all at the same time by typing my underscore x dot subs, and then in parentheses we give it a list with brackets, and within the list we have these parentheses with what each substitution is. And you can see it basically evaluates this expression each of these numbers substituting in. There's also an eval_f function that can be used to get numerical results. If I use the following expression, I can evaluate it making the substitution in the syntax shown here. This would be an example of a so-called Python dictionary. So the main functions that we've looked at so far are the symbols. We use that right up front to define the symbols we're using. The subs function to make a substitution. And then we've seen this eval_f that can be used. Simplifying expressions, we just use the simplify function. And we can use this to convert a string to an expression. So suppose I set a string, my string equals this mathematical expression. Then I can do my x equals simplify that string, and it stores the following symbolic representation as the variable my underscore x. And then if I want to substitute values in for that, I can do so. So it's pretty simple to use, hence the name, simplify my string. There's other examples that you can use. You can call it directly on an expression. You don't have to call it on a variable holding an expression. So in this case, simplify sine x squared plus cosine x squared, that's always 1, and that's what it gives us. If we simplify this expression, we get 1. If you simplify x cubed over x squared, then you can cancel those and we get just x. Or you can do my x equals x cubed over x squared and call my x dot simplify. So you can call it in two different ways, either on an expression, or if you've stored an expression as a variable, you can go my x dot simplify. There's a number of other functions available. The expand function. So expand x plus 1 times x minus 2 minus x minus 1 times x. And if you expand that, if you do the calculation and simplify it, the answer is just minus 2. You can also expand a generic product of two terms, and in this case it'll multiply through and just compute x squared minus x minus 6. There's the factor function, so if you give it a polynomial, this will do kind of the opposite of expand, and it will factor the expression and you get the factored version. There's lots of other functions available: collect, cancel, apart, trig simp, expand trig, pow simp, etc., and others. And the tutorial has a list of all of those and what they all do. You can do calculus operations in SymPy. So the main functions that we'll look at for the calculus are going to be this diff function for derivatives, differentiation, and then this is lowercase diff. There's also an uppercase derivative and a do-it function. So those are the three that we're going to be looking at for derivatives. The diff function, you give it an expression, cosine x comma x, and it differentiates cosine x with respect to x to give us minus sine x. If we have the derivative of e to the x squared comma x, then that would be 2x e to the x squared. We can also take a derivative multiple times. So if we want the third derivative of x to the fourth, we just say we're differentiating x to the fourth with respect to x and x and x. So the triplet here gives us this. This triplet here gives us the third derivative. We can also take a mixed derivative. So suppose the expression was we want the third derivative with respect to x, y, and z of e to the x, y, and z. This would work by simply writing, for example, my exp is e to the x, y, z, and I call diff my expression x comma y comma z. So first we take the derivative with respect to x, then we take the derivative with respect to y, then the derivative with respect to z, and this is the result that it gives us. The derivative function with a capital D and all spelled out doesn't evaluate the derivative, it's just used for making an expression. Then if we want to evaluate that resulting expression, we type do it. So for example, my underscore dir equals derivative of my exp xyz, then this is the expression. So it's not evaluated yet. And then if we type my dir.doit, then it will actually evaluate the expression. So calling derivative followed by doit is kind of like just calling diff. And the reason that you'd want to do that, obviously if all you want to do is evaluate the derivative, then call diff. But if you want to use derivatives in an expression, then this derivative function is useful. Integrals follow the same format. So there's integrate function, there's the capital integral function, and the doit function, and it parallels what we did with derivatives. So for integrate x squared with respect to x. That just gives us x cubed over 3 as we expect. If we want to integrate the following expression with bounds 0 to infinity, then instead of just typing x like we did here, we give it a list here of the variable and the lower and upper bounds. So here we go, integrate the expression, and then a list of the variable, its lower bound and its upper bound. Notice that infinity is noted by two O's. So OO together. It's easy to type and it looks like infinity, so that's the symbol that it's used for that. If you want to do a double integral, then you simply type in your expression and then x from minus infinity to infinity, comma, another list, y from minus infinity to infinity. It's fairly straightforward to give the expression, and in this case, this double integral evaluates to pi. Here's another example, my x equals integral of log x squared, comma x. There's the expression, and then if we do my x dot doit, it will go ahead and actually evaluate this integral expression. Same thing holds with limits. We can do that with limits also. In this case, the limit of sine of x over x with respect to x, and the limit as x goes to 0. So the pattern here is the expression, the variable, and as it's going to, what it's going to. There's another number of solver functions. So if we want to solve an expression like x squared minus 1 equals 0, we just type solve x squared minus 1, comma, x. And in this case, it gives us the two roots of the polynomial. The above was written assuming the form f of x equals 0. So all we wrote was x squared minus 1, and it assumed that we meant x squared minus 1 equals 0. If instead we had x squared equals 1, then in sympy we don't type x squared equals 1 to denote this expression. We use the eq function. And the reason is because Python sees an equal sign as assignment. So we'll use this eq function. So eq x comma y means x equals y. eq x squared comma 1 means x squared equals 1. So we can do solve eq x squared comma 1, and then comma x means we're solving the equation x squared equals 1 with respect to the unknown x, and it gives us the two roots. Or we can store that in an expression, my x equals eq x squared comma 1, and then solve my x comma x. We can do systems of equations fairly easily. So here's a system of two equations and two unknowns, x and y, and we can type solve. We type a list using brackets here, bracket x minus y plus 2, where it's assuming it's 0, comma x plus y minus 3, assuming 0, and then end the bracket, comma, and then another bracket x comma y, which are our two unknowns. And it outputs the results. And you can see it didn't output 0.5, it output it in a symbolic representation, which in this case was the exact analytic result, which was x is 1/2 and y is 5/2. We can also solve other equations. Here's an example here that you can try on your own. If you want to solve differential equations, then we need to use a function called dsolve. And we need to define a function symbol. So far we've only dealt with symbols like x, y, and z, which were just regular variables. But for a derivative we need to define a special function symbol. And it looks the same as what we did for x, y, and z, except that we add this CLS as in the class is a function. And so we just add this at the end, and now f and g are function symbols. So we can type f of x dot diff x, and it will do ddx of f of x. We can set up and solve the following second order differential equation by typing simply my differential equation equals this EQ sign. Remember, equality, the left-hand side, comma, the right-hand side. So in this case, we have f of x dot diff x comma x, that'll give a second derivative, minus 2 f of x dot diff x, first derivative, plus f of x comma sine x. We'll type in that expression, and if we look at it, this is what my diff EQ is symbolically in the solver. Then we can type dsolve my diff EQ, that expression. So solve that expression with respect to f of x, and it solves for the function f of x. So this will be really convenient if you want to find the analytic derivative, or the function given by a differential equation. We can also manipulate matrices, and there's a number of functions for dealing with these. We'll show a few of those. There's the main one is matrix, that defines a matrix, and we can see the shape of the matrix. We can access a single row or a single column. We can delete a column or delete a row, insert a column or insert a row. We can transpose the matrix. We can fill a matrix of zeros or of ones. We can make a diagonal matrix, find the null space, the eigenvalues, diagonalize it, reduce row echelon form, and a number of other matrix properties. So here's an example of finding a matrix, or of defining a matrix. We go A equals matrix, and then double bracket, a single bracket, where each one of these elements is a different row. So 1 minus 1, comma, bracket, 3 comma 4, end bracket, comma, bracket, 0 comma 2, end bracket, and all the brackets gives us this 2D matrix where we have the first row, second row, third row, similar to what we've seen before. We can also make a matrix that's just a single column. This will assume it's a column vector if you put it in like so, which is usually what we want. And we can check the shape. If we do a.shape, we can see that it's 3 by 2. That's what we get. We can access row 1. That's row 0. This is row 1. So that gives us 3, 4. We can delete row 0. A dot row del 0 gives us A. Note that this function does modify the matrix A. Unlike some other functions we've seen in Python that just return a matrix with that row deleted, this actually does operate on A in place. So that's good to know. We can solve an AX equals B system by typing x equals A minus 1 power to the minus 1 power times B. So if we do matrix A to the minus 1 power, that will find the inverse matrix, multiply it by B, and then we get x. And we can check to see if it recovers B like it should. A times x gives us 1, 2, which is B. Pretty straightforward to solve matrix that way. We can also do symbolic matrix solutions. So rather than operating on the numbers, we could operate on symbols. So let's define a bunch of symbols here. This would be like the elements of the matrix A. M11, M12, M21, M22 are symbols, and we give it the list of symbols. Same thing for the B matrix, B1, B2 is symbols. We form an A matrix out of that. A equals matrix M11, M12, M21, M22. B is matrix B1, B2. We can see A is now a symbolic matrix, B is a symbolic vector, and we can solve for x by going A.inv times B. And just for fun, we can see if it works to do the other approach. So if we do A up minus 1 times B, then we get the same thing. So there's this other function inv for an inverse, or we can raise it to the power. And this gives us the x vector, where the first element is symbolically this, and the second element is symbolically this, which can be convenient to have direct access to the matrix solution. So that's an introduction to using symbolic manipulations in Python. There's a good tutorial available, and it works for simplifying algebraic expressions, substitutions, solving calculus expressions, matrix expressions, and it's a pretty capable package.